Hey there folks, it's been a while since I've done a new video, so I thought I'd do a quick one, mainly as proof of life. In this video I'm going to talk about Donsker's invariance principle, a very beautiful result in probability theory. I assume some familiarity with basic concepts from probability, but I'll try to make the ideas as accessible as I can. Let's get started. Donsker's invariance principle is about Brownian motion. Before diving into the math, let's take a very superficial look at the history of Brownian motion. It's been around forever, but was first discovered in the 1800s by Robert Brown, a Scottish botanist, with pollen particles suspended in water. Brown was one of the first to use a microscope, and this allowed him to observe the highly irregular movements of the particles, which at the time was unexplained. This same type of behavior was later modeled by Louis Bachelier, a French mathematician, in relation to the movement of stocks. Bachelier is considered the founding father of modern mathematical finance. Famously, Brownian motion was later studied by Albert Einstein using statistical physics. He explained the movement of Brown's pollen particles as the result of bombardment by water molecules. This explanation provided strong evidence for the existence of atoms and molecules, which was later confirmed experimentally. The mathematicians Andrei Kolmogorov, Paul Levy, and Norbert Wiener made important contributions to the mathematical formalization of Brownian motion. And Monroe-Donsker proved an invariance principle showing that Brownian motion exhibits a type of universality, as we'll see. Donsker is photographed here on the right with the pipe. Do you recognize that person on the left? That's Veridon, another famous mathematician who collaborated with Donsker. Alright, that's enough about the history, let's get into the math. Let omega AP be a probability space and T a set. Here omega is a sample space, A is a set of events, formally a sigma algebra, and P a probability measure. T is thought of as a set of times, which might be discrete like the integers or continuous like the real numbers. A function x from omega times t to the real numbers r, which sends the pair omega t to the number xt omega, where xt is a random variable for all t, is called a stochastic process. Formally here, each xt is a measurable function. But intuitively, we think of xt as a random function of time t. For each time t, we have a random real number. Changing our perspective slightly, we can also make the set of functions from t to r, denoted r to the t, into a probability space, and we can think of the induced function x blank from omega to r to the t as a random function or random path in time. Notice that we've suppressed the subscript t in the notation for x blank, which I'll just call x. We can then talk about the distribution of x, and compute probabilities like this. Here C is a set of paths in R to the t, and we're computing the probability of x lying in C. For a concrete example, imagine that x represents the balance of your investment portfolio over time, and C is the event that you meet your retirement savings goal. This framework provides a mathematically rigorous way to quantify the likelihood that you'll wind up on the street. Brownian motion can be modeled as a stochastic process. Its distribution is called Wiener measure, which was proved to exist by Wiener, Kolmogorov, and Levy. Yes, that's really what it's called, and there's no shortage of puns in the mathematical literature. Brownian motion has many interesting mathematical properties, but we'll highlight just a few. First, it's a Markov process, which means that its increments are independent of the past, and in particular independent of past increments, which is one of the defining or characterizing properties. This means you can't predict how it will change from its past behavior. Second, it's a Gaussian process, which means that its increments, as well as its marginal or finite time distributions, are Gaussian, that is, normally distributed, as well as centered. In particular, in one dimension, if we assume that Brownian motion starts at 0, then at time t it's normally distributed with mean 0 and variance t. This is actually weird. The variance is proportional to time, so the standard deviation, or change, is proportional to the square root of time. Since the square root function is not differentiable at 0, this implies that the velocity of sample paths is undefined. Despite this, sample paths are continuous. So Brownian motion provides examples of continuous, nowhere differentiable curves, objects once seen as highly pathological in the history of mathematical analysis, but which are actually quite commonplace. Here's a graph showing an approximation of a Brownian motion path in one dimension. Notice how the curve is extremely wiggly. In reality, it's fractally so. If we were to zoom in on the real path, no matter how closely we zoomed, it would still look just as wiggly. That's why this graph is only an approximation. Finally, we can state Donsker's invariance principle. Let xi be a sequence of IID random variables in R, with mean 0 and variance 1. Recall IID means the variables are independent and identically distributed, which is why I can just write x when describing the distribution. Beyond having mean 0 and variance 1, we're not assuming anything else about this distribution. Let Sn be the partial sum x1 plus through xn. Notice that Sn can be viewed as a stochastic process in discrete time, where each point in time is a natural number n. The value of the sum goes up and down randomly over time as we add more and more x's. To get a process in continuous time, we can linearly interpolate between the discrete times as seen here, where the brackets denote the floor function. This new process agrees with the original process at natural numbers, but taking t equal to 1.5, for example, st is halfway between s1 and s2, and so on. Finally, for each fixed natural number n, we can rescale the continuous partial sum process up to time n so that it fits in the unit interval from 0 to 1, and then we can normalize it by dividing by the square root of n. Pause the video if needed to make sure you understand these definitions. The invariance principle says that these rescaled, normalized partial sum paths converge in distribution to Brownian motion. What does this mean? Informally, visually, you can think of these little partial sum paths going up and down randomly, getting more and more wiggly as they eventually converge to an infinitely wiggly Brownian motion path in the limit. But formally, this is a statement about convergence in distribution, not convergence of sample paths. In a certain sense which can be made precise, this says that probability statements about the partial sum paths become more and more like probability statements about Brownian motion as time goes on. As we noted, the invariance principle holds for any distribution of the x, provided essentially that there's a finite mean and variance. That's why the principle is universal, and why it's so powerful. As a corollary, notice that the convergence in distribution of the partial sum paths at time t equals 1 to what we know is a normal distribution is just the ordinary central limit theorem. As you may know, that theorem is of fundamental importance in probability and statistics, and we see here that it's contained in Donsker's theorem. For this reason, Donsker's theorem is sometimes called the functional central limit theorem. Isn't it a beautiful result? Alright folks, that's all for now. Here are the references I used while making this video. Thanks for watching.